Math 30-2. So we're going to continue our next chapter, or sorry, next chapter here, continuing this unit. So this unit's all about probability. It's going to tie in closely to our Venn diagrams we had in the previous chapter and our permutations and combinations in the previous chapter before that. So that's why this chapters 1, 2, and 3. If you're following along with the textbook, if not, that's okay. I'll give you questions online anyway. That's why these are all tied together as one unit. So in probability, just exploring, well, obviously the probability of something happening, an event happening. And then this page here, we have a bunch of terms here we're going to go over. Let's just explore this first of all. Look at this question here, what we have. So Mr. Allen and Mr. LeMace are playing a game that Mr. Allen invented. All right. There's a question later on you can see down here. It asks you, is this game going to be fair? Well, probably, since I invented it, it's probably not going to be unfair, but we'll see. So these are the rules. 2 people play. Each player has a container, so they just have a box. Right? Each player puts 3 identical slips of paper in it, numbered 1, 2, and 3, in their own container. So you have a box. Here's a box, right? Inside that box, you put slips of paper, 1, 2, and 3 in it. For each turn, players draw a slip paper from the container. Mr. Allen scores points if the product of the 2 numbers is less than the sum, and Mr. LeMace gets the point otherwise. And if there's a tie, no one gets points. So after each turn, the slips of paper are returned to the containers, and then you do this 10 times. And at the end, whoever has the most points wins the game. So the question is Mr. Allen's game fair? Now, to be a fair game, that's a very key point. Like, you might be asked this question later on. Oh, sorry. Still doing the same thing from before. To be fair, that means all the players have to have an equal chance of winning. Right? So like, you consider casino games and stuff, the house always wins because the game's not fair, because the house will win more times than the player. Okay? So in this game, because we have 2 players, Mr. LeMace and myself, do they have equal chance of winning? So we have to determine maybe the probability of each person winning the game. Okay, so before we go any further, let's talk about some terms that you might see throughout this chapter. So a trial, you see here, a trial is just a single performance of a defined experiment. So this defined experiment that we'd be doing right now, like this game that we're playing up here, we'd be drawing a slip of paper. That's 1 trial, and there's 10 trials in this game. An experiment consists of just multiple trials. So this whole game is an experiment because it has 10 trials in it. An event. So a collection of outcomes that satisfies a condition. So these are like up here. So my events, these here would be my events. If I want to highlight events here, these 3 things would be my events. Like either I get points, Mr. LeMace gets points, or nobody gets points. All right. Example of this would be like rolling a dice and throwing an odd number. So my events would be 1, 3, and 5. Right? Probability of an event happening. Right? So this is the key part. This is where the math comes into play. So when I would calculate the probability, we denote that by saying P of A. So that's calculating the probability there of event A happening. So one of those outcomes up there in that game, what's the probability of one of those things happening up there? Well, to calculate them, you take the number of times, assuming everything has an equal kind of chance of doing or coming out. You take the number of times that event happened and divide it by the total number of trials in the experiment. Right? Now, this is going to be an experimental one. There's 2 of them. There's a theoretical one, and then there's an experimental one. The theoretical one the experimental one is one you actually do. So I take my box, I pull a bunch of numbers out of it, I look at the outcomes, and I tally up how many of them were successful. So maybe like tossing a coin. You take a coin, you flip it a couple times, maybe 4 times, or out of 10 times, sorry, flip it 10 times. And out of 4 of them, you get heads. So 4 out of 10. 4 times you got heads. Let me just highlight that. So here you go, 4 times you got heads, and then 10 times 10 trials, and then you just reduce it down. So probabilities are usually written as a fraction, sometimes a decimal if you want to put into like a little box or something. Maybe if you put it into percentages, you can, but most of the times it would be written as a fraction, a reduced fraction as well. Okay, well, that's experimental. You could see that if I flip a coin, it should be, the probability of happening should be a 50% chance. It's either heads or tails. It's one or the other. See, my coin is not loaded or anything. I should get 50%, but you look at the numbers here, and I get 2 out of 5, so that's about 40% chance. Or 4 out of 10, I guess, could have gotten that 40% chance. So the experimental probability doesn't necessarily have to meet up with what you expect it to happen, just because of conditions that are beyond our control. All right, maybe the coin was loaded. Maybe the person's really good at flipping coins in such a way that it always lands a very specific way. So experimental probabilities don't usually match up with a theoretical one down here. Okay, so a theoretical probability, I'm going to skip past the sample space for 2 seconds. I'll come back to that. The theoretical one, same idea. So it's just the probability of the number of times that outcome could happen in this what we call the sample space. Now the sample space is all the possible outcomes. So say like on a die you have 1, 2, 3, 4, 5, 6, or heads you have 1, 2. You only have 2. So this here there's 2 in that sample space. There's 6 in this sample space. Okay. Now the number of favorable outcomes in that sample space, not how many times you actually do the trials and how many times you do the experiments, just how many are favorable in this sample space. So like when you flip a coin, there's only 1 head in my sample space. All right, that's a head, there's only 1 of them. And there's 2 in total in my sample space. That's why there's a 2 on the bottom, so it's 1/2. So maybe like probability of rolling a 1 on a dice would be, well, I have 1 in my sample space, and there's 6 of them in total. Or maybe I have probability of rolling an odd number on a dice or something. So if I look up here, there's 1, 2, 3 odd numbers. So 3 and there's 6 in total, so it's most likely a 50% chance or a half probability there. So when we're doing this to determine if it's a fair game, we want to look at the sample space. We want to look at this theoretical probability and say, is it possible for there be an equal chance to win, or maybe not? You might see some other things too, like an impossible probability would be the event doesn't actually come, or doesn't actually it's not inside the sample space. So like rolling a 0 on a dice, that's an impossible probability. Rolling a 7 on a single dice, unless the 7's on the dice, that's an impossibility. There's also other ones that we call a certain probability. A certain probability is that the probability of this event happening is 1. It's a 100% chance of happening. So maybe just like getting a number on the dice after you roll it. Okay, you're probably going to get a number on the dice. So I have 6 numbers and there's 6 in sample space. So there's a 1 probability for that. That's a 100% chance of happening. You might see this later on. We'll talk about certain probabilities, like when we talk about probabilities and talk about counter probabilities, the complement of that. Usually when you add all the probabilities of all the possible events together, you should get 100%. If you don't, then you're missing out on something we have to talk about. Okay, so we're going to try to determine, is this game fair? So I'm going to go down here, the next page here. I'm going to answer some of these questions here. So this first question here is, what we're going to try to do is playing the game once. So playing it, just an experiment, 10 trials, doing the game once. Is that a good way to decide if it's fair? It's probably not, because you're not going to get a situation where you get perfectly, he gets 5 wins, I get 5 wins. If that's the case, then it's a fair game. Most likely someone's going to win, right? If someone's going to win, then it seems like the odds were in that person's favor for that experiment. If you do it again, maybe the other person wins. Then maybe that kind of evens out, but maybe you keep on playing and I'll just keep on winning. Right? So there's no way to decide if it's fair. Maybe Mr. LeMace will keep on winning, even if the odds are in my favor. So is playing the game a good way to decide if it's fair? No, it's not. This will give you an experimental probability. I'm going to put a video in the link to this lesson that Khan Academy put on about experimental probability. It might be a good one. He talks about things that are out of control, and sometimes even playing the game 1,000 times doesn't even actually give us a good indicator if the game is fair. All right. So experimental probability is never a good decider. Okay. Seems like my writing's gotten worse today. Mr. LeMace here decided that you can use reasoning to decide if it's a fair game. So how he decides reasoning is a fair way to decide is that we're going to draw the sample space. I'm going to draw a bunch of boxes in this unit about the sample space. So this box that I'm drawing here is my sample space. It's all the possible outcomes that we could have if Mr. LeMace draws a card and I draw a card. So my two sides here. So I can either draw 1, 2, or 3. And Mr. LeMace could either draw 1, 2, or 3 from his box. And then we're just going to go through and decide what are all the different outcomes we can have. Okay? So we can fill in all these boxes, and we could just kind of mentally do some of these and say, okay, if the sum in this one, so add 1 to 1, so if we both draw 1, our sum is 1, and our product is 1. So if I go back to my rules, I win a game if the product is less than the sum. So my sum, so you could also just say the sum is greater than. So I'll win the game. Yeah. I'll win the game in this situation because the product is less than the sum. So I'm going to highlight all the times I win with the yellow here. Okay? So is the sum greater? So let's look at this next one here. Okay, so I can fill out this one. I can go the sum. The sum is 3. Product is 2. Oh, so I win again. In this case, the sum is 4. The product is 3. I'm going to win again. So I win in those 3 cases. All right. So if I win in those 3 cases, I'm going to go down the other side here. These rules are just the same here. So I got a sum of 2 or 3 and a product times them together of 2. So I win there. The sum of 4 and a product of 3. So I win here. So right now it looks like I win 5 times out of the 9 things in here. So it doesn't look very promising for Mr. LeMace. Actually, I don't think it looks very promising at all for Mr. LeMace. So let's go through the other ones. Let's see where LeMace could win. So maybe over here, let's try this box here. So LeMace could win in this box, I think. So because my sum is 5, but my product is 6. So the product's bigger. So Mr. LeMace wins there. The product's 9. The sum is 6. Mr. LeMace wins here. The product of 3 and 2. So I'm just multiplying those two is 6. The sum is 5. So Mr. LeMace wins. And the one in the middle, no one wins because that's 2 and 2. So that's 4 if I add them, and it's 4 if I multiply them. So no one wins there. So the probability that Mr. Allen is going to win me is if I look at this, because remember our rules for this, I'm going to take the times that's favorable in my outcome, so 5 times, and there's total sample space here of 9. There's 9 boxes. So that's 9 fifths, or fifths 9, sorry. And for Mr. LeMace to win, he's going to win 3 times out of 9. I'm going to reduce that one down to 1/3. Now, usually it's hard to look at fractions and say, are they comparable? So I'm just going to put them in decimals. So this is 0.33. So about 33% of the time, Mr. LeMace will win, and I will win approximately 56 times. So because these are not even, the game is not fair. There's also a chance it will tie as well. You can see that there's a 1 in 9 chance that will tie. Who's most likely to win this game? Mr. L. Because I made the game. Well, I didn't make the game. I found the game. I just said I made it. Okay. So we're going to go through and you can decide out of these three. So I want you to pause this video and just decide, are these games fair? Okay, give it a try and I'll be right back. Okay, so hopefully you try them out. Now, a good way to determine if they're fair or not is to draw out their sample space like we did before. So Matt and Pat here tossed a coin, each tossed a coin. You can either land heads or tails, and here's heads or tails. So I'm just going to list off my sample space here. So either I have heads and heads, or tails and tails, or heads and tails and tails and heads. So those are my two things. Matt wins if they're both heads or tails, so Matt would win in this one or this one. And then Pat will win if it's tails and heads. So Pat will win in that situation. So they each have a, so if I took the probability here, the probability of Matt is 2 out of 4. And the probability of Pat is 2 out of 4, which is a half for both these cases. So yeah, this is a fair game. Okay. Now Trina, Lena, and Gina toss coins, and they have the same kind of idea, but this time Trina wins if they all land heads. Lena wins if they're all tails. Otherwise, Gina wins them all. Okay, so we go through their sample space here. So our sample space is a little bit more crazy. I'm not going to be able to draw a box here, so I just have tails, tails, tails. Okay, then I have heads, heads, heads. So these are my two situations for Trina and Lena. Then my other situations here, I got either tails, heads, heads. I have heads, tails, heads. Then I have heads, heads, tails. So that's 3 situations. Then I also have heads, tails, 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 heads, tails, and tails, tails, heads. So I have those as well. So here, Gina is going to win in all of these spots. Trina wins if they land all heads. And Lena wins if they all tails. So I could see that this is not a fair. It's fair between Trina and Lena, but it looks like Gina wins most of the time. So this is not fair. Okay. Sometimes the sample space gets a little bit large if I were to try to draw them out. So here we got, they roll a standard die. So remember, a standard die is from 1 to 6. So I'm going to draw this sample space for this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then I'm going to draw out a few lines here. And then we're going to talk about patterns in this thing. And you're going to see these patterns pop up a lot. Makes drawing out these sample spaces a little bit easier if you see the patterns. All right. So here's my sample space. On the top, I have Anne, and the side I have Dan. Doesn't really matter who's on which side here. And then we want to determine if the sum is greater than 7, Anne wins. And the sum is less than 7, Dan wins. So we got to figure out all those numbers. Now, a couple of good patterns that you see on these is this one, not the 2 here. One thing is that you can never get less. If you roll the 2 dice, you can never get less than 2. That's a good thing to know. But if I do this, I go 3, and they just keep adding 1. So this is a good pattern. 2, 3, 4, 5, 6, 7. 7 is the highest number we can get on this side up here. But I can go all the way down to 12, though I can get to 12 that way. But then you can see this pattern pop up. So if I have 3 here, I'll have 4 and 4. And you can see that as it goes down diagonally, the numbers are all the same. So 3 and 2 gives me 5, 2 and 3 gives me 5, 1 and 4, yep. So this one here, 4 and 2 give me 6, 3 and 3, 6, 2 and 4, and 1 and 5, 5 and 2, 3 and 4, 4 and 3, blah, blah, blah. And then if I continue the pattern, 8, 8, 8, 8, 9, 9, 9, 10, 10, and 11. Okay, so I've drawn out my sample space. Looks pretty good. Now I want to know when Anne wins. So when is Anne going to win? She wins when it's greater than 7. So she's going to win in all of this right here. And Dan's going to win when it's less than 7. So Dan's going to win in that area there. And then nobody wins in the 7s here. So all these 7s here, no one wins in that spot there. So if I look at this, yeah, it's being cut perfectly in half. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so they both have a probability. The probability Anne winning is 15 out of the 6 times 6. That's 36 ways. And then the probability of Dan winning is 15 out of the 36. So this is a fair game as well. Pretty good. Yeah, so I'm going to finish up this page, finish up this video here. So I'm going to give you guys just think about what is the probability. I want you to try these questions out. I'm going to pause the video again. I want you to try this. I want you to pause the video and try these questions out. I'll come back. All right, welcome back. So let's see what we got here. So a fair dice is rolled. So that means that all the sides are equally probable to pop up. Sometimes you can have loaded dice. What's the probability of rolling? A factor of 6. So let's look at the numbers of 6 first. I want to know what the factors are. So 1 and 6 and 2 and 3. So these are all the factors of 6. These numbers are on the side of the dice, 1, 2, 3, 4. There are 2 more sides on the dice that we don't have here, 4 and 5, to make our total 6 sides. So the probability of getting a factor of 6 is what's unfavorable. We got 4 sides that give our factor of 6. The 6 in our sample space, we can reduce that down. So we'll divide both sides by 2. 2 and 3. So it's a 2/3 chance of getting a factor of 6. Probability of a circular spinner with 4 equal sectors. What's the probability of landing on a heart? All right. So there's 4 equal sides: clubs, diamonds, hearts, and spades. One of them is a heart. There are 4 hearts. So it's a 1 in 4 chance of getting a heart. Okay. 3 coins are thrown, and the number of 2 heads and 1 tails is counted. What's the probability of getting 2 heads and 1 tail? So these are 3 coins again. So we did this with the Trina, Lena, and Gina example. So I'm just going to write out our sample space. So those are all tails, all heads. We have this one, we have that one, and we have heads, tails. Okay. And then we have tails, tails, heads, tails, heads, tails, and then heads, tails, tails. Okay. So I look at my sample space. It looks like all the different ways I'm going to write this. I want to know when we have 2 heads and 1 tails. So those are those 3 right there. So the probability of this happening, let's just call that event A. Let's label that event A. So 3 times out of the total of 8 possible ways in our sample space. So the probability was 3/8 there. Okay, the experiment consists of rolling a 6-sided die, flipping a coin, and a spinner divided into 5, hopefully equal regions here. The number of elements in the sample space would be what? So let's this is for that number that would be on the bottom of our probability here. So if I were to try to create the sample space, I'm going to have quite a bit of things. It'll be like a cubish kind of shape to it. There's going to be lots of things in there. I can create this by using a tree as well. So if I have the dice, right? 1, 2, 3, 4, 5, 6. And then I can roll a 1 and then flip a coin and get heads or tails. But I can also, if I rolled a 1 and got a heads, then at the end of that, I can have 5 regions here. We can call this A, B, C, D, and E. So right there, I have 1. 1 of my sample space could be a 1 on the dice, a heads, and an A. A 1 on the dice, a heads, and a B. A 1 on the dice, a heads, and a C. So these are all different things that can happen. Right? Now I could do the same thing with the tails. I can have a 1 on the dice, a tails, and an A, a 1 on the dice, a tails, and a B. It's going to be a little bit, it's going to be a lot because I'm going to go here 5 times. I'm going to go here, a heads and a tails. So I'm going to have like a 2 on the dice, a heads and an A 2 on a dice, and a heads and a B, dot, 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 et cetera, et cetera. Then I can have a 2 on the dice, a heads or tails and an A 2 and a dice, a tails and a B. It's going to be a lot here. It's going to be 5 there. It's going to be another 5 here. All of these are going to have the same thing. So what we can do is we can use the fundamental counting principle. I have 6 choices for the dice. I have 2 choices for the coin. And then I have 5 choices for the spinner. Then I can multiply them all together and I get 60. So 60 elements in my sample space. So I wasn't going to list them all, but you can see that up here. That started getting a little bit more than I can actually handle, and I can probably start counting them out and then start crossing them off. Like that was definitely more than 3, definitely more than 7. By the time I got to the heads here, the 2 heads one, I'm past 15. So the only choice I had was 60. Okay. This case here, we're just trying to figure out which of these would not be included within my sample space that we have. So we have a kind of a weird side. We have a 5-sided dice. 2 sides are labeled 1. 1 side's labeled 2. This is the red dice. I should mention this is the red dice here. 2 sides are labeled 2 and 2 sides are labeled, oh, sorry, 1 side's labeled 2 and 1 side's labeled 3. Now, okay, I'll just keep on going. Then we have the green dice. Each side is labeled a 1, 2, 3, 4, 5. We only use 1, so that just makes sense. This is standard dice. Okay. So we're going to go through and just try to figure out, okay, which one of these could not be in my sample space. If I were to try to list them all off and have like a little tree of everything, which couldn't exist. So if I look at the green dice here, so my green dice, 2, 3, 4, 5. Okay, those numbers exist because on the green dice I have 1, 2, 3, 4, 5. So these numbers could exist on the green dice. But I look over here, 1. Yeah, 2 sides are labeled 1, so that side could exist. So I can have a 1 and a 2 possible. A 2 is on my dice. You can see over here, there's a 2 here on my dice. There's a 3 on my dice, but my 5-sided dice doesn't have a 4. So I can never have a 4 on the red and 5 on the green dice because this 4 does not exist. Okay. Okay, so the next video, what we're going to do here, we're going to be talking about odds, the different types of odds, and how we represent odds in favor and against. But that's the next video. Try out the question practice sheets that are also linked with this video, and I'll see you next one. Bye.